Yes, and we're recording. Okay. So brief recap, just to have to be sure that you have all the right formulas in the slides. So this is how we calculated a scattering cross-section for a single particle. We knew that um, the product of the scattering cross-section times the incident intensity equals the scattered power. We can calculate the scattered power by putting the particle at the center of a hypothetical sphere. Some way get an expression for the scattered intensity from that particle, and then integrate. If we integrate that scattered intensity over the area of that sphere, then we also calculate the scattered power. So by equating these two, we can solve for the scattered for the scattering cross-section of the single particle. Now, if we had n identical particles, then under the assumption of no phase relations, then the total scattered intensity was n times the scattered intensity of a single particle, so that the total scattering cross-section in the volume V is then n times that of a single particle. So the total scattered power, that is what the equation says as well. The total scattering cross-section is then found by first using the expression for the scattered intensity of one particle. So that was the distribution function s squared divided by the wave number, and then integrated over the area of that hypothetical sphere. So the total scattering cross-section was then became simply n times the scattering cross-section of a single particle, and we can so let's a little bit trivial extension of that formula. In the box is the same formula that we ended on with in the last slide, but now I can add the part in green using the phase function. So the phase function of a single particle integrated over 0 to pi sine theta d theta, and also integrated over 0 to 2 pi d phi, but because there is no dependence on phi in the phase function, that gives you the factor 2 pi. The phase function by definition was a joint probability density function for scattering into angles. So that means that written this way, this has to evaluate to 1. So that's the reason it is a little bit of a trivial extension, because you just multiply the right-hand side with 1. But this is a useful notation for later, so that's why I have it here. Then the scattering coefficient, the density of scattering cross-section, as it is defined, is taking the total scattering cross-section and dividing it by volume, and that gives you the density in the expression. Okay, we had this. That leads up to this, of course, that the assumption that the phase differences on average are not 0. That is usually not true. If people do that, they say, yeah, the particles are randomly placed, so you can always find this matching pair of particles that cancel each other. But under these constrictions that we might have, that is not the case. What we'll see is that the phase difference between two particles depends on your angle of observation. That is then the scattering angle theta, under which you observe the scattered light, and the distance between the particles. Can be expressed as the inner product of two vectors, the vector q and the vector rij. The vector rij is the vector that connects both particles, and the scattering vector q is the factorial difference between the scattered wave vector and the incident wave vector. So that is ks minus k1. I have a lot of typos to correct, I see today. Ks minus k incident, for which we'll get an expression later on, but that will depend on the scattering angle. So let's look into that further. The first assumption is that all scatters are identical, and the second assumption, the first Born approximation, that they are all illuminated by the same field. They all experience the same field. They all experience the same intensity. So let's draft an expression again for the scattered intensity in this case. So the total scattered intensity is then again the sum of the individual fields of the scattered fields of the individual scatterers multiplied with its complex conjugate, and then averaged over larger volume. So that sum in the brackets can be so you add the field and then multiply the complex conjugate, or as written here, we square the field, so we can then write this term as a double sum, so running over all particles. So if E is J, then we're looking at the same particle. So then the expression is simply E squared is the intensity from one particle, because in that case, if I is J, then the phase terms cancel. And for all the other combinations where I is not equal to J, then there is a phase term appearing, which is given by this exponential. So that's given here. So this would lead again to what we had on the first slides. This whole series of intensity 1 plus intensity 2 plus intensity 3, etc., and then the whole bunch of cross terms. So the cross terms are where the phase difference is actually still there. So now we can consider the terms where E is J, so where you're essentially looking at the same particle, and the terms where E is not J, where we're looking at cross terms. So we can calculate. We can consider them separately. So if E is J, then we just get n terms of E sub I times E sub I again. Complex conjugate, so the phase terms cancel. So that gives rise to the term here, the first term on the right-hand side of the lower equation. So n terms that are all equal because particles are identical of E particles squared. And then here is the terms where I is not J. So if you look closely, then you see that in the iteration of the sum of the second sum. So the first sum runs over all particles. I is 1 to n, and the other one also runs over all the particles, but it accepts the case when J is equal to I. So that is the notation for that. So that gives rise to these terms. We can rearrange that a little bit. We can because we know that if the particles are identical, then the amplitudes, the scattered amplitudes of even if you look at the cross terms, is also going to be equal to the intensity of a particle because they are identical. The amplitudes are identical, so we can take that out of the equation and then rearrange. We get we find this expression. So we still have n times the intensity of the particles, intensity of the scattered intensity from the particles. Here we would have the intensity outside of the sum, because that would be an intensity equal because the particles were equal. So if we divide this by the number of particles, then we can bring that even before the brackets. So that means that we now have an expression for the total scattered intensity that is equal to our previous result. So simply n times the scattered intensity from a single particle, and then times this new factor. One simply maps this one, of course, and this term here, this double sum term here, is the term that counts for the interferences. So you have basically the exponential here is the phase difference between the scattered fields from a particle pair I and J. What you have here is basically the average phase difference, of that collection of particles, and that is called the structure factor. So this term between the brackets. So that is basically the term that describes the deviation from the ideal situation where all the phase differences would cancel, the term outside the brackets, and this is then kind of a correction term, or like kind of a correction term that accounts for interference effects. So it depends on the phase difference between the particles. That phase difference, as I announced, and as we'll see a little bit later on, that will depend on the scattering angle, or the angle of observation theta. So this structure factor can then be written as a function of theta, as of theta. Okay, then the ISJ terms are usually called the independent terms independent of phase. Basically, there is no phase information in there, and the terms for ISTA are dependent. They are dependent scattering terms. They depend on phase relations between particle pairs. Okay, so now let's see if we can find an expression for the phase differences, phase difference between two scattered fields. So this is going to be the situation. I'm going to rotate this figure a little bit later on, but just to quickly outline the arguments. So we have two particles here. These are the orange dots. The incoming field here along wave vector k0, and then scattered field towards the detector ks with the wave vector ks, and by that definition, the angle here between k0 and ks is the polar scattering angle theta. So we're looking at scattered light in this direction. We assume again that the field amplitude in both incident on both scatters is the same. So the first Born approximation, and then we can calculate. The phases of the incoming field is the same as well on the left-hand side of the picture. And so then the goal is to calculate the phases of the field scattered from both particles somewhere far away here at the detector. Now we're only interested in the phase difference, so we can look at the differences, and then the phase itself is k, the wave number times the distance. So in this case, we can calculate the phase difference by simply looking at the geometrical difference of the paths from let's say the source to the detector. So a lot of that is just the same. The difference lies here. So for the lower particle, there is an extra distance traveled, a traveled here towards the detector compared to the top particle, and for the top particle, there is an extra distance b traveled there from the source to the detector here. So the difference, the phase difference, is then k, the wave number 2 pi over lambda, times the length of this segment b minus the length of this segment a. That is the phase difference. So what we have to do is use a little bit of geometry to actually calculate the length of these segments. Wait, I'm not going to spoil it already. Okay, let's try. Rotate it for convenience. I've rotated the geometry a little bit. This is the first particle illuminated with an incoming field, and there is an outgoing or scattered field in this direction. Then we add a second particle. The incoming field comes along wave vector k in, so that is now denoted here in bold because it is a vector. The scattered field, the outgoing field, is here denoted by k out, also bold because it is a vector. And then the distance of the vector that connects, and that should be bold as well, between the two particles is called r. Okay. Then the angles in this problem are the scattering angle theta, so that is by the definition the angle between k in and k out and k in, and then so the angle then between k out and this dotted line over here, and for that we can using that dotted line we can define an angle epsilon here between the line here between k in and the vector r that we can use later on. Okay, now let's add the second particle. So that is then of course at the end of the vector r, the vector that connects them. We have k in here as well, parallel to the incident vector here, and the scattered the outgoing wave vector is of course parallel to the outgoing wave vector for this particle as well, because we're looking at this from a very large distance, so we can take them. We can take them parallel. So we're looking at large distances, but we're only interested in the difference. So that is then the goal. This is the phase difference that we need to calculate. So the phase difference is k, the magnitude of these two wave vectors. 4 wave vectors. We're looking at elastic scattering, so there is no transfer of energy. So the magnitude of k in will be the same as the magnitude of k out. Only the direction is different, but the magnitude is the same. So k times then the distance in the length of these two segments, B and A. So for A, we can write, if we define an angle alpha here between A and R, we can write A as R times cosine of alpha, and cosine alpha can be written as the inner product of two unit vectors, a unit vector along R and a unit vector along EN. So we can write A as R times this inner product, the cosine between these two. We can do the same thing for the segment B. So we define an angle beta between B and the vector R. So there too, B, the length of B is now R times cosine beta, and cosine beta can be written as the inner product of two unit vectors ER, again along R, and a unit vector along the outgoing wave vector. So combining that, we get our first expression for the phase difference. So filling that in the top equation, k times b minus a becomes r times k. So the r carries over from the a's and b's, the k carries over from there. So r times k, and then the inner product of the unit vector along r with b minus a. So that is the difference, the unit vector difference in the outgoing direction, the scattered direction, and the incident direction, the incoming direction. Then this k can be combined with the unit vectors e out and e in. So basically, if we multiply the unit vectors with the magnitude, then we just get our vectors k out and k in back. So now we can write it as r times then the unit vector along the r direction, inner product with k out minus k in, the vector k out minus k in. Or if we keep using unit vectors, then it becomes r times unit vector in the r direction times k times magnitude q times eq. And I've defined here the vector q now as the vectorial difference between k out and k in. So if you draw that, then k out lies here, minus k in lies here. So the vectorial difference between these two is this vector q, so-called scattering vector. That seems to point to nowhere, but it's the vectorial difference between k out and k in. So this expression. So we've solved part of the problem. The only thing that we now have to do is, if you really want to calculate the phase difference, so let's assume that we know what the distance between the particles is. We now have to calculate the magnitude of the vector q. Of this vector q in order to calculate the phase difference. So we shifted the problem a little bit. I'm not going to dwell too much on that, but you can draw a parallelogram that uses the vectors k out and k in, and that has the vector q along its shortest diagonal. For that, you can use the cosine rule to calculate the length of that diagonal that is given here in terms of unit vectors. And if we write that in terms of the magnitude of k, then the result is the length of q is going to be k, the magnitude of k, times the square root of 2 minus 2 cosine theta. So that is this theta that lives here, but also here. That one we can manipulate a little bit. We know that the sine squared of let's say sine squared of x is 1 minus cosine 2 theta divided by 2. So we can rearrange that a little bit to replace the cosine term, and then because we now have sine squared, we can take that square root and manipulate that into this expression. So 2 times k, that the k is carried over, times sine half theta. So this is the magnitude of this vector q. And that means that we're almost done now. So this phase difference, again, the intermediate steps, k phase difference k times the length of b minus the length of a was could remanipulated into an expression r times unit vector in the r direction, inner product q times the unit vector in the q direction, or if you like, just the inner product of the vectors r and q, and the magnitude of this vector of this phase difference then is the magnitude of r, so simply the distance times the magnitude of q is 2 times k, the wave number 2 pi over lambda, times sine half theta. Okay. So basically, what we now the important result is now we have calculated an expression for the phase difference between two particles, and indeed, as I promised, it is a function of theta, of the scattering angle. So now let's see what happens. So I'm going to show you a few simulation results of scattering calculations using two identical particles. So we can calculate the phase difference using what we just derived. And what I'm going to do is I'm going to calculate the scattering cross-section, the total scattering cross-section of the two particle system. So that means that I'm going to calculate the scattered intensity of these two particles, taking into account this possible phase term, and then sphere around it, and then integrate over that sphere to get the total scattering cross-section of the system. And I'm going to normalize that on the scattering cross-section of an individual particle. So in that case, you can see whether or not the scattering cross-section of the increases or decreases compared to when there was no phase difference at all. And these particles are identical. So what you'll see here is what the graphs will show is the total scattering cross-section of the system divided by 2 times the scattering cross-section of a single particle. Can do that for to start with for 2 configurations. So both have an incoming wave vector in this direction, and the first system has 2 particles aligned at a certain distance r, aligned along the wave vector, along the incoming wave vector. And the second set of simulations has the particles aligned distance r apart, but then perpendicular to the incoming wave vector. So these will give you know now by the construction of the vector q that they will give different phase differences. And the calculation is done using mean theory for particles that have a diameter much less than the wavelength, particles that have a diameter almost approximately equal to the wavelength, and particles with a diameter much larger than the wavelength. So that's going to be 3 curves, and then all as a function of particle separation. So first, this is the graph for the system where the particles were aligned along the incoming wave vector. On the horizontal axis, you see the distance between the particles normalized on the particle radius, and on the vertical axis, you see this normalized scattering cross section. So the total scattering cross section divided by the 2 times the individual cross section. In red here in red is a forbidden region. So for distances up to 2 times the radius or 1 times the diameter, the particles are that's not allowed because they are not allowed to overlap. But you can, as the graph shows, you can still perform the calculations as if it were allowed. But for interpretation, you should basically ignore the part within the red bar. Okay, then this is a calculation at 632.8 nanometer. That is a red helium neon laser for the particle diameters of 200, so much nanometers, so much smaller than the wavelength. 600, almost equal to the wavelength, and then 1200 nanometers, which is much larger than the wavelength. And you can see some different effects. So if you go along the horizontal axis, so start just outside the forbidden region, then there you have the situation where the particles are touching, and then as we move along the horizontal axis, the distance between the particles increases. And then looking at the scattering, the total scattering cross section, the normalized total scattering cross section, you see that if the distance becomes very long, you cannot see it, but I think you will believe me if I say then that this normalized scattering cross section goes to 1. In that case, the interference effects will be negligible, and the total scattering cross section is just going to be the sum of the individual scattering cross sections, as if there were no interferences for the two identical particles. So that should go to 1. But if they're close, you can see that this interference actually really matters. So remember, the interference can be constructive, it can be destructive. So anything can happen. But you can see here that for the close distances, for the larger particles, there is quite an amount of constructive interference between the scattered fields, which basically leads to a total scattering cross section of the system that is larger than the scattering cross section of the individual of the two individual particles. You see the same thing for the particles that have a diameter that is almost equal to the wavelength, albeit at a little bit lower magnitude. And at the for the smallest particles, there appears some oscillations that is really interesting. I'm not entirely sure. I did not look into detail at what that causes, but usually what you see is that for small particles, the diffraction, so scattering, as you remember, is a combination of reflection and refraction and diffraction. For the larger particles compared to the wavelength, the diffraction is the dominant phenomenon, and for the smaller particles, the refraction is the dominant phenomenon. So I guess that has to do with these oscillations showing up for the small particle and not for the large particle. Then, if we look at a situation where the particles were separated at a distance that was perpendicular to the incident wave vector, then we see some similarities, but also some differences. Of course, again, there is this forbidden region where the particles are not allowed, so we ignore that. But now, if we look, for example, to the smallest particle, if they are very close, we find a number that is less than 1. So in this case, the interference is destructive. So the total scattering cross section of the system appears less than the scattering cross section of the two individual particles. And then again, that happens for for the small particle, you get all these oscillations again. For the larger particles, the effect is also there. So at short distances, if the particles are at short distance, then the destructive interference between the fields causes the total scattering cross section to be less. And then if you increase the distance, then these effects become less and less and less important, and then it goes asymptotically to a value of 1 again. And then finally, to see what happens when the particle. So let's say the second particle can have any orientation with respect to the first particle. So what we can do is simply average the scattering cross section over all possible orientations. So because of symmetry, that means that if we just place the second particle along such an arc, we get we can calculate that. And then you see actually the effect of averaging over different orientations. So you see that the interference effects become much less pronounced. So again, a forbidden region. For the smallest particle, you see a slight effect here, where there is a little bit of oscillation and a little bit of a little bit of amplification. So constructive interference. And for the larger particles, for this two-particle system, you actually don't see much effect anymore. Right. So let's then armed with that knowledge, let's go back to the ensemble of the n scatterers that we had an expression for. This total scattered intensity was n times the intensity of the identical particles of a single particle. and then times this structure factor, which had here in blue the phase difference now filled in. So Q, the inner product of Q, factor Q times of inner product times the factor that connects the particles, and here it is still written as Ri minus Rj, but that is the factor that connects both particles. And Q is now, we know now, is the magnitude of Q is 2 times K, wave number 2 pi over lambda, times sine half theta. So if we now go through the conventional way of calculating the total scattered intensity or the total scattered power, we take we put the sphere around it and we calculate the power flowing through an area, and then from that we can solve for the scattering cross section. So we can do this for this ensemble now as well, for the total scattering cross section. And basically we had in the expression for the total intensity, we had this extra structure factor term. So now we have to include that into the integral. So the parts in black are simply the expressions that we had for the single particle. So the S squared is the redistribution function for a single particle, but now we include this S theta in the integral to account for these interferences. And again, if this if you would have the situation where all these phase differences average out, that means that the second term within the brackets will average to 0. So you're only left with this 1 here. Structure factor will be 1. So in that case, it would be that would be just a 1, and you have the old expression again. But this is the more general one then. So then now we can manipulate that also a little bit further. So as I'm sorry, somehow the font has shrunk a little bit. I hope you can see it. So this function S squared theta over K that we found earlier, that was equal to the scattering cross section of the single particle times the phase function. So we can substitute that into this integral. And so we have then the phase function of the single particle over here. The scattering cross section of the single particle is a constant. All the particles are identical, so we can take that out of the integral. So then rearranging this becomes the total scattering cross section is n times, for the n particles, n times the scattering cross section of the single particle. So that is what we had before, and now this extra term that contains the phase function from this manipulation, and that still contains the structure factor. So to calculate the effects on the total scattering cross section of these interferences, what you have to do is you multiply the phase function with the structure factor and integrate that out. So if the structure factor would be equal to unity, then it just is an integral over the phase function, which is normalized by definition. So then the result is 1. If the structure factor isn't equal to 1, then the integral therefore will also be will not be equal to 1, and that will be then the correction that you apply to the total scattering cross section. Actually, what we'll see in most cases, for at least for these soft materials like these spheres and for tissue, that integral term will be less than 1. So effectively, you will find a total scattering cross section that is less for the ensemble, that is less than the sum of the individual scattering cross sections. That is the same slide. Yeah. So then that was the total scattering cross section that now has this correction term. That means that for the scattering coefficient, which was the density of scattering cross section, so we divided by volume V, that term of course just carries over, and then n divided by V is divided by the volume is the density rho. Rho times the scattering cross section of a single particle would be the scattering coefficient that we would find when no interferences are present. So I'll call that the independent scattering coefficient. And then this again is the same correction term that you apply for the dependent scattering. All right. Is that clear so far? So we that we have the structure factor that basically describes our scattering. Okay. Then one brief sidestep again back to these statistical dynamics. Because we've been talking about organization and how because the particles are not allowed to overlap, there is some phase relation. And on one hand, we started with this pair correlation function that described what happened in the on the particle level, let's say. From the other side, we had this structure factor, which is the one that we actually need. To describe the effects on light scattering, but both were somehow had to do with positions and differences between positions. So of course there has to be some connection between this pair correlation function and this structure factor. So to see that, we can briefly go back to this description of the pair correlation function. But first, define an operator, a density operator, which is a little bit of a strange way of putting it, but that's how it's defined, which essentially counts the particles. So it is a sum of delta functions. The delta function gives you a 1 when the position that you look at coincides with the position of a particle, and otherwise it is 0. So if you do that for all RIs, for all particle positions, then basically you will get a count in the sum for each particle that you encounter. So this density operator here simply counts the particles. So if you then take the volume average of this density operator, then you count the particles and you divide it by the volume for the volume average. So that result would be n over v, and that was simply the density, the global density rho. So this volume average of this operator, or this volume average of this train of delta functions, gives you the density. You can do a similar thing, but now for the two particle distribution function. So that was a rho of R1 and R2. We can use the same. So for the single density, we had this expression for the two particle density. Do the same thing. So that means taking the operator running over a coordinate r, taking the same operator for the second particle running over a second spatial coordinate r prime, and then taking the volume average. So that is the middle term in the equation. And then on the right hand side is filling in the definition of the delta functions. So we now have two delta functions that count particles, both run over spatial coordinates, and only when Ri and Rj coincide in these two counts, then you will get a 1, and otherwise you will get 0. Why this elaborate function? Well, you can show that for a let's say we take a function, an arbitrary function phi, that is a function that depends on the distance between two particle coordinates only, so only on the distance. If you take a volume average over that of that function, you can rewrite that using these delta functions as such. So on the right hand side, the averaging runs over that same volume, and these delta functions only yield a 1 value of 1 when r and when this one hits r and this one hits r, and r prime hits rj. You can put that then into an integral, because only when both delta functions are 1, then you select an argument. So basically you can put these integrals around it, and these delta functions assure that you will only count them when the values match. So that's why these two sides are equivalent. Now you can change the order of summation and integration. You're allowed to do that. So then now the integrals are on the outside. So a double integral over r and r prime of this function. and then doing the averaging only over the delta functions gives us back the result of the previous slide. So the what was it? This two-body distribution. Sorry, this two-body distribution function over here equal to this double sum of delta functions, and that is what we now have here. So what is then the result? The result is that so to calculate basically to calculate the average of some function that depends only on the distance between particles, we can take that function over here, multiply it with this two-body distribution function, and perform an integration to calculate that property. Now, for this homogeneous isotropic medium, we had that for this two-particle density function was equal to rho squared, the density, times the pair correlation function. So we can make that substitution as well, and then the whole thing simplifies to this expression. So again, we have a function phi that depends only on the distance between two particles. If we take the volume average of that function phi, then we can express that in terms of the pair correlation function. So if it only depends on the distance, then phi of r is actually a scalar function over here. G of r was the pair correlation function. We have to perform a three-dimensional integral. We do that in spherical coordinates. There is no dependence on theta and phi, so that gives you the 4 pi factor here, and then r squared dr is the integration over the over radius. And of course, we have been looking at one of these functions, namely the phase difference between two particles. That was a function of the distance between two particle positions only. That phase difference we expressed as exponential I q and an inner product r, q the wave, q the scattering factor, and r the factor that connected both particles. But this is an inner product, so this in the end will be scalar. So that works. Now, if you now look at this briefly, look back at the right-hand side of the top equation. That was, as I said, it was a three-dimensional integral over spherical coordinates. And that because there was no theta and phi dependence, reduces to a single integral with a prefactor 4 pi. But if we now try to convert this back, briefly convert this back to the more general form, so the more general form being a three-dimensional integral over a three-dimensional factor r, which again in spherical coordinates would look like this. So now let's factor this integral back into that form. So then we have n times rho, these stay, and then this integral, this three-dimensional integral over dr, and of course the functions did not change, so they are still they still have a scalar argument, but in any case this now signals a three-dimensional coordinate. Now, if we fill in our expression for Vr, so the phase difference between two particles, then the result is this. So the integral of the pair correlation function times exponential minus I times inner product Q and R. Do you recognize this expression somehow as something?
Well, the absorption intensity was also an exponential.
Yeah, that's true. But this now is a complex one. No, it's I'm thinking a whole different way. This is a Fourier transform. This is just a definition of a Fourier transform. So what we see here now is the Fourier transform, the three-dimensional Fourier transform of the pair correlation function. So that means now so this was a rework of the right-hand side of the top equation. Here on the left-hand side we had the volume average of this function phi, which means in this case the volume average of the phase differences. So the average phase difference, which was a term that we had in the structure factor. So now we have on the left-hand side something that relates to the structure factor, and on the right-hand side we see that it corresponds to the Fourier transform of the pair correlation function. Yeah, so yeah, grouping that together, then on the left-hand side you have this this average phase difference, and on the right-hand side you have the Fourier transform. And just this was the expression for the structure factor, so it is similar. It's not entirely equal to the left-hand side of the top equation, so we have to manipulate that a little bit. We have to divide everything by n and then add 1 to it. That's easily doable. So then we have on the left-hand side now we have actually the structure factor as we defined it before is 1 plus rho times the Fourier transform of the pair correlation function. So that is how these are related. Now there's one more manipulation step to get to the definitions as you will find them in a textbook. What we can do is we can rewrite the pair correlation function as g of r minus 1 plus 1. And then split the integral in two. So gr minus 1 is going to be the argument of one of the integrals, and the one that we have to add back is going to be the argument of the second integral. So gr minus 1 plus 1 is the same as gr. Why this? Oh yeah, okay. And if we then so the first term is simply still the Fourier transform, but now of gr minus 1. The second term is the Fourier transform of a constant. That will be a delta function again. So this last term would yield rho times a delta function of q. So that will be one only. That will be equal to rho when q is 0, and it will be 0 at any other value of q. Q is 0. Q was 2 times k times sine theta times sine half theta. If theta is 0, then q will be 0. If theta is 0, then we're looking in the forward direction. So this term corresponds to what you measure in the forward direction. And actually, this is the term that describes the non-scattered light. So the fraction. So let's say you have some scattering efficiency q. That meant that the portion q of the incident power would be scattered, and therefore a fraction 1 minus q will not be scattered, but will just pass through. This is the term that describes that. So no change in direction, but actually no interaction at all. So therefore, we usually just omit it from the definition because we only are interested in the scattered light. So that delta term going forward will be gone and will be ignored. So then this is now our new definition for the structure factor as the Fourier transform of gr minus 1. Of course, this also has a component in the forward direction, but that is actually and that also corresponds to theta is 0. But this is actually the fraction of the light that is scattered, but is scattered in the forward direction. So in the forward direction, you have two contributions. You have a contribution of light that has not interacted at all, so it's just a fraction of the light that just passes through, and you have a fraction that is scattered, but then in the forward direction. So that is still contained. In here. So that then it adds up. All right. So then same equation. This structure factor S of q or S of theta on the left-hand side is given by the 1 plus the density times the Fourier transform of gr minus 1. This is if we look at a homogeneous isotropic medium, discrete random medium, as we were doing, then g of r will just have scalar arguments, distance r, and that means that since the inner product of q and r is also it's simply q times r times the cosine between these two factors, that is also just a pure number. So this whole thing will evaluate to something that is that has a scalar argument as well. Even though we do have to perform a three-dimensional integral, the argument on for the structure factor will also be scalar. So it will only depend on the magnitude of k. So 2 times 2 pi over lambda k times sine half theta. Yeah, there it is. So only on this this as a pure number, not a vector. And then rho, of course, was related to the volume fraction. So you can write this. You can write this also in terms of volume fraction if you like. And one way of expressing that is that the structure factor, so S of Q, as you would formally get it through this Fourier transform, is actually can actually be written as S as a function of theta, the scattering angle, and a function of the volume fraction, because it scales here with density. Okay. See how far am I with my slides. Now let's take a 15-minute break, and then we'll go to the last part of the lecture. So let's start again at 11.